Hi everyone, my name is Jigar Bhati. I'm a staff software engineer at Twitter. So I work in a CockroachDB slash NewSQL team at Twitter. We are a team of 6 engineers and 1 manager. And our goal is to productionize strong consistency solutions at Twitter via CockroachDB. So today I'm going to be talking about certain success stories that we had for productionization at Twitter. So I'm going to keep it very generic instead of diving deep into its specific use case. And I'm going to keep it more like read heavy use case, write heavy use case, and the multi-region use case. So the first 2 use cases that I'm going to be talking about, those are all like single region use cases. And the last one is going to be a multi-region use case. So let's dive into that. So the first one is read heavy use case. Let's talk about the topology first. So in this particular use case, the topology that we have used is a single region setup on the on-prem data centers. So we have 2 on-prem data centers in this example, and those are like independently set up CockroachDB clusters, but they are very identical to each other in the sense that the cloud data center is used for writing purposes, and that's going to be writing to both the CockroachDB clusters on-prem. So they'll be storing the same data, which is going to be used in the local data centers of Twitter for reading purposes. Now let's talk a bit about workload, and then we'll talk about the challenges and the learnings that we got out of it. So in terms of workload, since this is a read-heavy use case, we are talking about almost like 100 k QPS in terms of read at peak, and each QPS is 100 keys per query. And the entire cluster is set up with 36 nodes per data center, and each node has 40 cores allocated to itself and the associated memory and disk capacity. But the cores is like the main aspect of it. And in terms of latency, we are mostly concerned about the follower read latency in this case, and we were able to achieve less than 10 millisecond P99 follower latency. Now, this is the most interesting part of the talk. So I'm going to be talking about like what are some of the challenges and learnings that we got out of productionizing this use case. So the first one is we wanted to achieve 20 millisecond P99 read latency with a 99% read success rate, including the failover. So failover here means that there are other data centers, and Twitter generally does fail out of traffic from a data center into another. So we need to account for that increased traffic as well. So to be able to achieve this, like such a good latency and success rate parameters, we wanted to like we dove a lot deeper into like how do we actually achieve it. And the way we were able to achieve it was providing a single range solution. And what does it mean to have a single range solution is basically it disabled all the load based range split in CockroachDB. And what that provided us is it completely stopped the read fanouts. So for example, if you have multiple ranges in a 36 node cluster, and if you're doing a query which has 100 keys per query, then it can potentially fan out to 100 different ranges, which might be living into different nodes. And because of that, the latency could be increased. So we didn't want to have that to meet the success criteria on the latency. So we completely disabled the load-based splitting for the ranges. And the reason we were able to do this is we also have a very minimal storage footprint. So we are talking about less than 500 MB of total data in the cluster. And this is primarily because the use case is only looking for last 1 hour's data. So any historical data which is written before that, they are not really concerned about it. So we also set the GCTTL seconds to be 60 seconds in this case. And that's how we are able to keep the storage footprint pretty low. And the range size typically in CockroachDB, like the maximum one default that comes with it is 512 MB. So you're easily able to fit it into a single range solution. Uh, so that's one part of it. The another part is we set the number of replicas to be equal to the number of nodes in the cluster, which is equal to 36. And we set the number of voters to be 7 in that, where all the other nodes access non-voting replicas. And the reason we did this is, so whenever a request hits the CockroachDB cluster, it hits the gateway node first. And then the gateway node, based on the keys, it decides where the ranges are located for those nodes and tries to get the data out of it. So there's an additional network call that happens. But we wanted to prevent that to meet the latency criteria. So we made sure that all the gateway nodes are able to act as a replica nodes as well. And since we are talking about follower rates, This enabled us to do all the reads locally from the same node. So that's another aspect. And the last one is, since the amount of data is pretty small, we were able to serve majority of the reads out of memory. So there were like very few disk reads that were happening at that point in time. So one of the questions that people may have is, what about like the scalability perspective as the use case grows? But this use case is more estimated to be stable over like a foreseeable future. So that's not really a concern for this use case at this point. Good. Let's talk about another challenge. So the other thing that we noticed during the dark launch of this cluster was cluster meltdown. Uh, Specifically talking about the number of connections that the client instances make with the CockroachDB clusters. So just to give you an idea of scale, we are talking about 15K client instances, which are making a total of 360K connections to a 36 node CRDB cluster. So approximately 100K connections per node, per CRDB node, you can think of it like that. So because of the sheer amount of connection scaling, um, at peak load, what we observed was due to client-side interrupts or timeouts, it can potentially happen that those interrupts causes the connections to be broken down and rebuild that connection, leading to connection churn with the CRDB server nodes. And because of that, the CRDB server nodes would, even connection building is pretty expensive. So because of that, it will see high CPU overload, ultimately leading to cluster meltdown and stability issues. And the reason for that is CRDB does not support pre-auth connection level rate limiting at the moment. So there's no like real connection level rate limiting that can be provided by it. So it tries to accept all the connections that it receives, sometimes overloading the CPU. So that's a problem. Uh, but the good thing is CR Labs is already working on it, and sometime soon this feature will be available. Uh, so for the time being, the fix that we did was to do client-side rate limiting to restrict the max connection request per client instance can make to the CRDB cluster. So that's one part of the fix. And the other part is we also defined grace period before the connection cancellation. So we at Twitter use Finagle Postgres for connection building purposes. And that does not support. So, for example, let's consider a case where we have client-side timeout set to be 20 millisecond. We have server-side timeout set to be 40 millisecond. So in that case, we can set up grace period to be, let's say, 80 millisecond. And that way, even if there is a client-side timeout, it will allow until the grace period before the connection is cancelled. So that server gets a chance to respond back saying the statement timed out or whatever. In the cases of, some of the queries taking longer than estimated time. So because of that, we don't. The client is not triggering any connection cancellation, and the same connection can be reused for sending other parts of the request as well. So that helped reduce the number of connection churn from the client side, and thereby like reduce the connection request the CRDB server was getting, and thereby improve the stability of the cluster. Um, and we set the statement timeout to be 40 millisecond on the server side, just to prevent any long running queries that may be triggered, in an ad hoc fashion or something. And the bottom graph, you can see like the scale at which the new connections get created under this high load. Cool. So that was the success story for the read heavy use case. Now let's talk a bit about the write heavy use case, where the majority of the traffic is write, whereas reads are pretty low in the order of like tenths of requests per second. Again, the format is going to be pretty similar. We'll talk about the topology, we'll talk about the workload, and then we'll talk about the challenges. In terms of topology, it's exactly similar to what we had before, where the cloud data center is trying to write to on-prem data centers in the CockroachDB cluster, which are very independent but identical with each other in terms of the data stored in it. And the reads will be done mostly on the on-prem data centers. Cool. Let's talk about the workload now. We had a 64 nodes cluster per data center in this case with 32 cores assigned per node. And we were using 21.2.5 CRDB version. We were using default application factor, which is 3 for user tables and 5 for system tables. And in terms of achieving the success criteria, we had a throughput success criteria here, which was most important, where we wanted to achieve a continuous import within 6 hours, which roughly translated to 500K write QPS for this use case. And we are talking about approximately 1 TB storage footprint. So this is more write heavy and storage heavy as compared to the previous use case that we talked about. And in terms of latency success criteria, We wanted to achieve less than 100 millisecond P9 write latency and 99% success rate to be able to achieve the 6 hours import SLA that we have defined. And what we actually were able to achieve was less than 65 millisecond P9 latency. And we were able to complete the import within 5 hours and certain number of minutes. So that's pretty good. Okay, and now let's talk about the challenges or the learnings. So the first issue that we observed was cold start issue. So this term is mostly derived from like how cars behave during winters when there's like a lot of snow. It takes a lot of time for the car to warm up. So similarly, if a CockroachDB cluster is has a table which is newly created and no traffic has been sent to it, it can happen that when you try to hit that table with a large amount of QPS, which is on the order of 500K, right? QPS in this case, 90% of the traffic gets sent to the one set of replica or the one range that the table is initially assigned with. And that can lead to cluster stability issues. And we saw P99 latency as high as 5 seconds. So it was not acceptable for us. So we tried certain things, but that didn't work independently. So for example, the natural thing that comes into mind when we have a single range to begin with is how do we make sure the range gets split faster, and how do we make sure the ranges are transferred between the nodes faster. So those are the two things that we tuned. We tuned the range split QPS threshold to trigger the faster range splits, and we also tuned the snapshot rebalance rate so that those ranges will be transferred between different set of the nodes faster, that by achieving horizontal scalability instead of one node taking the majority of the traffic. But that didn't work fine for us independently because the rate at which we were throwing the QPS was too high, and the CockroachDB could not catch up with that QPS to be able to do this rebalance and split faster. And that still had like cluster stability issues. So another set of things that we tried was using splitat, which is used to pre-split the tables into a predefined set of ranges. So it typically works like you create a table, it has only one range to begin with, and you define certain range boundaries based on which this table will be split into. But again, defining those range boundaries can be a bit tricky, and the amount of traffic each range may not be very equally distributed. So another thing that we tried was alter table scatter command, which triggers distribution of leases and replicas. Um, but even after doing that, if you see like there's a leaseholder and count image below, we saw that some of the leaseholders had lower number of ranges, whereas some of the leaseholders had higher number of ranges. So even after doing all this, we were not able to get like equal distribution of range across the different nodes that we have in the cluster. So ultimately, it led to some of the nodes running hot on CPU as compared to the others, leading to inefficient resource utilization. Then we worked with CR Labs to come up with a different solution, one of the possible solutions as well, where they recommended to use 22.1.0 CRDB version, which had a fix to minimize this delta QPS between different nodes that we have in the cluster. But there were certain issues with that as well. So if you look at on the left side of the graph, we have the average queries per node and the CPU percent for 22.2.5 version, and the right side the same thing for 22.1.2 version. So you can see the average queries per node definitely got much better with the newer version, but the CPU percent, even though it looks better, there's still a variance of 15-20% from the nodes which are running very hard as compared to the other nodes in the cluster. So definitely it was one of the possible solutions, but again, we wanted to see if we can still optimally utilize our resources in terms of CPU percent, because that's like the core aspect of CRDB licensing as well. So what ultimately we ended up choosing as the final solution is we did automated slow ramp up on client side to give CRDB enough time to do the splits and also do the range transfer or range distribution between the nodes. And we used whatever setting we had done before for the range split threshold and the range snapshot transfer rate threshold to be able to do this as fast as possible. So we had like a period of 30 minutes or 45 minutes where the traffic gets slowly ramped up in percentages of 10, for example, and then by the end of 30 or 45 minutes, it will reach the 500K QPS for the write. And over this period of time, CRDB has enough time to actually do the range splits and transfer that without causing any CPU overload issues or cluster stability issues. So if you can see like the average number of queries per store was pretty well distributed. Even the CPU looks pretty well distributed, 80% for all the nodes. And this is more like an independent Kubernetes related finding that we had. So initially, when we deployed, we did not have the liveness probe disabled. So under high QPS, what used to happen was certain nodes would fail the liveness probe checks, thereby causing them to go down and affecting the cluster stability. And CR Labs also recommend to have this liveness probe disabled. So we as soon as we enabled that, like disabled the liveness probe, it definitely improved like a cluster stability. So that was a big learning as well. Good. Let's talk about the final use case, which is the multi-region use case. Again, talking about the topology, this is more like a typical multi-region setup where we need to provide global consistency across all the data centers. Writers could be anywhere, readers could be anywhere, and we still want to provide global consistency. And this is set up in such a way that a replica will be present in a few replicas will be present in each of these data center, um, so that we can actually provide the global consistency. In terms of workload, we have 36 nodes clustered across the data centers, so 12 per data center, and each node has 32 cores per node. We are using 22.1.3 CRDB version, and the replication factor we used here is 7 for both user and system tables. And I'll get to it, like why we chose 7 in a bit. In terms of throughput success criteria, we have 40K reads, and mostly all of them are follower reads. Some of them, like very small percentage, is strong rates. And even in rates, approximately 90% are point rates, and approximately 10% are scan with a batch of 50. And we wanted to achieve less than 200 millisecond P99 read latency here. And for writes, we have approximately 4K writes. Again, 98% is single row writes, and 2% is batch with a set of 50. And we wanted to achieve less than 500 millisecond P99 writes. And this is all writes are all like global strong consistency across data centers. In terms of challenges and learning, so again, we had to do a lot of connection tuning here as well to find the optimal connection count per client instance to not affect the cluster stability. Uh, I won't go too much into details because you already talked about it before. And the next one is primary region setting. So by default, this multi-region clusters follow the workload topology in CockroachDB. That is basically like the region which gets the most traffic. CockroachDB will try to move the leaseholders toward that region and kind of moves automatically in between the regions. But if you have like couple of regions which are very close to each other, then you can potentially use the primary region setting to define, one of the regions is primary region, and then it will, whatever request comes to it, it will try to form a quorum with the closest another region, and that minimizes the network latency needed to complete a request. So we ended up using primary region setting where we defined the primary region to be the one which is closest to the other region, thereby satisfying the quorum sooner, and that helped a lot in improving the latency as well. Also, if you have that region which is taking majority of the traffic, or that those two set of regions, then also it's like a very good setting to use. The third one is we also removed foreign key constraints. So this is something that our use case was okay with, so we went ahead with this. And the reason being, for insert, when you try to write a record into a table which has a foreign key reference to another table, which may be assigned with another ranges, which might be living into another node. So because of this internode communication, this can cause network delays, and also this locking can potentially delay the request satisfaction. So we ended up removing that as well. And from Kubernetes perspective, as I said, like I'll be talking about why we chose RF7. The reason being the pod disruption budget that is defined, it's at a single region level. And let's say we have 3 regions, then it is quite possible that one node in each region can be taken down for maintenance purposes. So we need at least 4 more to satisfy the quorum. And that's why we went ahead with RF equal to 7. And another option is to build a custom pod disruption coordinator, which looks at the regions and makes decisions to be able to take down only one node at a time, and that we can achieve RF equal to 3. But that's something we haven't implemented yet, but it's definitely in our future work. So yeah, that's about it. Thank you everyone. And if you have any questions, then yeah, we can discuss them after the talk.